Okay, good morning, everyone. Let's get started. So just remember, tomorrow is the deadline for homework 0. If I'm yet started, please do it right now. Otherwise, you may get panic for that last day. Okay, and also try to leverage office hour. We got, I believe, 4 hours or 5 hours of office hour tomorrow. If you do have any question, please do not hesitate to stop by. Okay. So let us continue the basic knowledge review. In our last lecture, we talk about definition of the convex function. So first, convex function must be defined on convex set. So what is convex set? We talk about the definition on Tuesday, that we say a region or set of points as convex, meaning that if we pick up arbitrary 2 different points in this region, if we draw a line connecting these 2 points, no matter, remember, this has nothing to do with the dimension. No matter which dimensions those 2 points stay in, like 4-dimensional, 5-dimensional, even 10-dimensional, you can still draw a line connecting them. Like if and only if every point on this line or segment still stay inside this domain or region, we call this region as a convex region, right? So I gave a counterexample, like for this kidney shape, like if you pick up 1 point X here and 1 point Y here, you draw a line connecting them. You see this red segment, they got outside of the domain. So this domain is not convex region. Okay, and then if we can define a function on some convex domain, and we have additional requirement. That is, if we pick up arbitrary 2 inputs from the domain and pick up arbitrary ratio, which is between 0 and 1, if this inequality holds, then we say this function f is convex, right? So literally speaking, it's saying that, okay, we're going to first do the left-hand side, right? We're going to first do the convex combination of x1, x2 according to t, and then evaluate this location, right, of this function, right? And this function value should be less than or equal to, we first evaluate the function values at x1, x2, then do the convex combination according to t, right? So it's a little bit tedious definition, but if you just contrast it to some figure, it will be very, very clear, right? So this curve, this black curve, is a typical convex function, f of x, right? So it can take arbitrary 2 points, 2 inputs here, x1, x2, leaving the x-axis, right? We can take arbitrary t, right? So according to the left-hand side, if we first do the combination of x1, x2 according to t, because t is between 0 and 1, so the combination must stay in between x1, x2, right? And now you evaluate the function at this combined location, you get your function value here, right? That's where your left-hand side tells, right? What your left-hand side tells, right? So if you look at right-hand side, right? If you evaluate x1 and x2 first, you got function value here and here, right? Then we consider combining the function values according to t, which is what the right-hand side tells, right? So if you combine the convex function values according to t, I mean, geometrically, it's very easy. You just draw a line and just do this parallel line, right? So this is where your convex combination of function values at x1, x2. You see that this combination of function values actually is bigger than the function value at the combination of the inputs, right? Which reflects the definition here. So actually, for this particular function, you can choose whatever 2 points, 2 inputs which are not overlapping, right? You can try to do that. You always find this this inequality is correct. Right? So then we claim that this function is convex. This is a definition. Okay? So in practice, there are many functions which are convex. For example, If x is a single variable, like exponential function, is convex, negative logarithm of x is convex, x squared is convex, right? And you can also extend definition of convex function to like multidimensional inputs, right? For example, here x is vector, then a linear function, which people also call it affine function or convex, right? Quadratic functions are convex. There are many, and including the examples listed are almost zero, right? So one question is that how do we determine a convex function? Right? Giving you a function expression, right? How do we claim that this is a convex function or not, right? So we can show this, we can check if it is convex by just testing this inequality, right? But sometimes it is non-trivial to verify the definition directly. So we can use these following two most common used checking conditions, right? So first one is that if your f of x is differentiable, then if you can show that for arbitrary x and y, you got fx is always bigger than or equal to fy plus this dot product between the gradient at y and x minus 1. So I want to ask, what does the right-hand side mean geometrically? Any thought? Right, it's just to stimulate our memory, right? What does the right-hand side look like? Yeah, it's a line, of course. What kind of, what's the speciality of this line? Any thought? What's the special stuff? What's the special thing about this line? It's not an arbitrary line. Yes, exactly, right? So look at, we got our slope is the gradient, right? So it's a tangent line. And you see that this tangent line actually go across y and fy, right? So if we take, this is a function of y, right? Sorry, it's a function of x, right? So if you take x equals to y, then the value of this line is fy, right? So actually it overlaps with the function f at y fy. But then because its slope is a gradient, right? So it means it's a tangent line, right? Maybe this is more concrete if I draw a picture, right? So suppose this is your f of x, right? You pick up arbitrary y here. See, this is your y, right? So the line expressed on the right-hand side here actually is the tangent line which pass through y and fy. Right. Just to give you some geometric intuition about that, because later we're going to talk about how do we construct a lower bound for a convex function so that you can do some subgradient descent. And subgradient descent is also you couldn't call it tangent line because it is possible that your convex function is not differentiable, but as long as the line is below the entire function body, you can view it as a generalized tangent line, and you can use that gradient. You can use their slope as some subgradient. We're going to talk about detail later, but here let us just give you some kind of impression here. So if f of x is twice differentiable, then if you can show that f of x, the Hessian of f of x is a Hessian matrix, right, is positive semi-definite, then we can claim that f of x is convex as well. So you can pick up either conditions here, right? To test if a function f of x is convex or not, you just need to test if one condition is satisfied. If it is satisfied, then it's convex function. Okay? And if you're interested to know like how we can derive that from this inequality to the definition of convex function right here, right? You can check it online, or I'll find it in any convex optimization book. It's very, very fundamental. So I will leave it as an exercise for you, right? If you're interested. So any questions so far? Okay, great. And associated with convex function, there's another famous inequality. It's called Jensen's inequality. Suppose you got function f convex, right? And now let us consider a random variable x, right? Jensen's inequality tells us that if you take expectation over x and then evaluate f at expectation of x, it will be upper bounded by you take expectation of f of x. So you can see that when you swap expectation at f, you're gonna have an inequality, right? And this applies to any function over x. Like suppose you got another function g, and then you got g of x, which is another random variable. Now you apply Jensen inequality, it still holds. So the function of expectation of gx, g of x is less than or equal to expectation of function of g of x, right? So this is a very, very useful result, because it forms the foundation of the variational inference, which is kind of like, I guess, is the most fundamental algorithm in modern machine learning, like variational autoencoder, all kinds of stuff, stochastic variational inference, and so on, right? So the construction of the learning objective for variational inference is based on this Jensen's inequality, because really we're going to look at the logarithm of the probability, which is called log likelihood, log joint probability, and if you take negative of log probability, if you take negative of logarithm of some function, is a convex, right? Then you can apply this Jensen inequality to get some bound. Like, no, G can be arbitrary function. Yeah. It just needs, we just ask that f must be convex, right? G can be arbitrary valid function, right? And then you just apply this Jensen inequality over g of x, because g of x is also a random variable. Any question? Everyone's comfortable? Okay, great. So the last piece I want to piece of basic knowledge I want to mention is a matrix derivative, right? So we got one problem. I think the last problem, our homework 0, ask you guys to try your best to work out some matrix derivatives. If you feel confusing or feel extremely difficult, don't get scared. You can either do the original definition, right? In our calculus 1 or calculus 2, you must know that, okay, if I got a function of a vector, right? Suppose this is a vector, right? This vector has multiple elements, right? You got x1, xn, right? So you know that the gradient of the function with respect to x will be a set of partial derivatives, right? The partial derivative of f with respect to every element in x, right? So partial f. Forgive my awkward drawing, but I just want to deliver the meaning, right? So you can just follow the very preliminary definition of the derivative, vector derivative, and just calculate that and then form that. That's fine. And if you want to use some more advantageous tricks and notations, you can take a look at this matrix derivative literature, right? I give the links here, right? So basically, matrix derivative is the same as function derivative, right? Remember the derivative, the definition of derivative, right? It's the first order approximation of a function. Right? So for any function, according to Taylor expansion, we know that it can be written as if you expand it at some particular point x0, so you got fx0, then you got the gradient of f at x0 times x minus x0 and plus some high order term, which is x minus x0's I think it's just a higher order than first order, right? So the derivative is just here, right? This is derivative. Sometimes it's also called gradient, but it's kind of like exchangeable, right? So if your x here is not a number, right? It's a vector. We know that it will becomes a dot product or inner product, right? If your x is matrix, so this will be matrix difference, right? The difference between two matrices, and then this one should be matrix as well, right? And then the dot product between the matrices, people usually use the trace operation to represent that, right? So that's how these results come out, right? So if you use this same viewpoint to look at the derivatives, then vector derivatives, matrix derivatives, and number derivatives are the same. The only difference is that, okay, I'm gonna think about whether I'm gonna use trace or use dot product or just use numbers to represent all this, right? And in fact, in most of the cases, you even don't memorize that. You just need to look up some dictionary. So here we list a set of most commonly used matrix derivative rules, right? So if you take a derivative over a constant matrix, it'll be simply 0. 0 means 0, a matrix filled with 0, right? If you take a derivative over a constant scalar alpha times a matrix variable x, then you're gonna first take the derivative over x and multiply alpha, which is the same as all the rules you have learned before, right? And this is just like the derivative of two matrices or vectors. Their addition is equal to the addition of their respective derivatives, right? And there are a bunch of other rules, like this is very similar to the derivative rules for the product, right? And there are some kind of like rules which you might have never been saying, be able to say for matrix operations, like this N1's product, right? This is a Kronecker product, right? But they all have their own rules, right? You don't need to know, you don't need to prove why this is work. This has already been summarized by those pioneer mathematicians, right? You just apply it. Yeah, so if you want a full book of all kinds of matrix derivative rules, this matrix cookbook, which was assembled by University of Toronto many years ago, will be a very, very useful reference, right? Again, we hope that you will be able to use those rules to solve the last problem in our homework 0, rather than just following the original definition. Right? But again, it's up to you. Any questions so far? Mm-hmm. I would say rigorous proof means that, okay, for example, if I want if the problem is asking you to show the convexity, right? And you can either follow the definition, say, okay, if for arbitrary to x and y, your f over a convex combination of xy is less than or equal to the convex combination of fx plus fy. That's one way. Or you can use the two other rules we mentioned, right? You can show fx is always less than or equal to some tangent line or that, or the hash matrix is always positive semi-definite. You show either of them, you can conclude that, okay, this is convex. Other question? Okay, great. So now we have we haven't finished the introduction about our course and basic knowledge review. Oops. We're gonna start with the supervised learning framework. Okay, so next we're going to talk about supervised learning framework and decision tree representation. Right. So as we mentioned, right, the overall semester we're going to mainly focus on supervised learning framework because it is most important, it is mostly used, and if you know well about supervised learning framework, it's very easy for you to transit to unsupervised learning or even semi-supervised learning. Right? So today we're going to talk about the general settings of supervised learning. And I'll give some warm-up. We're going to introduce decision tree representation to give you a concrete idea about decision trees, definitions, and some general properties. And next lecture, we're going to jump into the decision tree learning algorithm, which we call ID3. Right? So first, what is supervised learning? Right? Literally speaking, it's like, okay, you got some teacher, right? The teacher will teach you what is right, what is wrong, and you learn from your teacher's experience, right? So it is kind of quite consistent with our like intuition about this, right? So I'm gonna use some particular application to illustrate the supervised learning, right? So suppose we got some task, right? Want to develop a machine learning algorithm to automatically tag news articles. So you know, we got like millions of news articles every day, right? And of course, want to classify those news articles into different categories like entertainment, politics, sports, finance, and so on, right? And then every particular news article can be viewed as an instance, right? As an instance that needs us to tag or classify. Right? And each instance, we're going to assign one label, which can be sports, can be business, can be politics, can be entertainment, and so on. Right? So that basically describes our task. Right? You given some particular piece of a news article, right? You run an algorithm, you want to tag it into one of a few categories, right? So naturally, we can view all possible news articles we want to tag as the so-called instance space. Right? So what does instance space mean? It's just a collection of all possible instances you want to classify. And accordingly, all possible labels, you might use them to tag your instance. It's called label space. Okay? And your algorithm development essentially is to find a way to learn a mapping from the instance space to the label space. Does it make sense? Right. So now let us give a little bit formal definition, right? So to conduct supervised learning, right, we're gonna first define two spaces. First is called instance space. Instance space is a set of examples that need to be classified, right? For example, if you learn batch game, right? If you still remember, we play this a mind game. It's called batch game, right? Then the instance space might be the set of possible names, right? If you want to classify the documents or newspapers, then the instance space could be the collection of possible documents, right? If you want to do the spam email detection, then the instance space may be all possible emails. Right? And then you also need to define what is the label space. As the name suggests, right? Label space is the set of all possible labels. It also closely related to a particular task you want to do. Right? So if you want to do the email spam filtering, then your label space is just binary, spam or non-spam. Right? If you do just a binary classification, right? Positive examples, negative examples, we got in general two labels, positive and negative. Right? If you do the news tagging, then the label space is a set of tags you would like to assign each news article. Right? Any questions so far? Okay. So then we're going to assume that this is our fundamental hypothesis. Okay? We're going to assume that there is some magic underlying function which maps the instances from instance spaces to labels in label space. Okay? We denote this target function by F. And the goal of learning is to find out this target function, or at least find out some good approximation to this target function. So you see that actually it's very hard to exactly recover the target function. In practice, right, in most cases, we just expect us to find a good approximation to this target function. We'll explain the reason later, right? But right now, just let us to keep this in mind, right? The learning essentially is to find out or approximate this target function, and thereby learning essentially is a search procedure, right? Searching over some functional space and to find some function. Okay. So what is supervised learning? Supervised learning means that the learning algorithm only sees examples of function in a finite number of cases. More specifically, supervised learning assumes that, okay, you have collected a set of examples which consist of pairs of input, pairs of instance, and the label of the instance generated by this target function. Okay. And we call this data set as the training data. Okay. And once you have collected the training data, you feed the data to some learning algorithm. Okay. And the learning algorithm is in charge to search over some functional space, right? And guided by this training data to find some function. Okay? And this function we call it the learn function G, right? Which is also mapping from the input instance space to the label space. Right? We expect that G should be at least close to F. Right? In the ideal case, it will be like, okay, G will completely recover F, right? But in practical perspective, we just expect G to be as close as possible to F. So now we can see the whole supervised learning protocol, right? We define the instance space, we define a label space. Our hypothesis is that, okay, we got an underlying function which can do the labeling over those instances, right? And then we prepare a labeled training data set, right? We feed this training data set to some learning algorithm, which could be SVM, it could be deep neural nets, it could be whatever else, right? And learning algorithm will return you a learn function G, and we expect that G is close to F. Does it make sense? Any questions so far? This is like simple framework actually summarizes most machine learning algorithms. Mhm.
Is there any way they would like learning algorithm figure out how generate the data?
Yeah, that's a good question. That's actually the topic of machine learning. Like people when they develop a learning algorithm, like as you said, like you will first figure out, okay, if I know the mechanism to generate those labels, right? For example, I can fabricate some underlying target function F, right? And then I test my learning algorithm to say if my learning algorithm can reverse engineer the mechanism of F, right? That would be good, right? But there are other branches or methods that they say, okay, as long as you give me enough data, even my learning algorithm totally black box, I can still recover that. I can show that. It's called universal approximation, right? But in practice, like this is meaning for like research, right? If you apply it in practice, it's pretty hard to get every details about how this target function works. Like you don't know, like we know that human beings, when we look at a picture, right, we know that it contains cat or not, it contains human faces or not, right? Everyone has such kind of ability. However, we just don't know how we get this ability. Right? We don't know how do we process those RGB pixels and form some kind of shapes, and then we can classify the patterns. Right? We just don't know how our brains are working. Any other question? Okay, so now let us think about other protocols. Right? This is one protocol that I prepare a set of completely labeled training data set, and then I feed to some learning algorithm. I get some a learning function G to approximate target function. Is there any other learning protocol? Mm-hmm. Oh, okay. Yeah, I think you're talking about the learning procedure, right?
Yeah.
Some kind of iterate procedure you might like dynamically feed the data to the learning algorithm. Sometimes the reinforcement learning framework is called feedback, right? You're gonna run some trajectory according to feedback, you're gonna generate another trajectory. Yeah, this is definitely another learning protocol, right? Any other thought? Okay, so we're going to introduce other simple protocols, right? We haven't, we're not going to talk about reinforcement learning. It works another semester. Mm-hmm. Yes. This is something we're going to discuss. We're going to talk about right now, right? So we're going to give you some examples of learning protocols in terms of the data set. So what if I just prepare the instances? Right? I don't prepare the labels, right? Can I still feed this unlabeled training data set to some learning algorithm and learn some function? The answer is yes. Right? And this is called unsupervised learning. Okay. Meaning that I don't know the actual label, what the actual label is for each instance. I still want to find out some kind of classification some kind of mapping which maps each path maintenance to one class or one tag. Right? This is called unsupervised learning. And the typical methods is called clustering. You got K clusters. Actually, you're meaning I got K classes, I got K tags, right? I want to classify each instance into one of those K clusters, meaning that I'm gonna assign a label on them. And I can also make a hybrid of labeled training examples and non-labeled training examples. Right? And this is called unsupervised learning. Right? But again, we're gonna focus on supervised learning. Just to let you know, like we got other learning paradigms, but they're, I mean, in the most general framework, they're close to each other. Right? They all have like instance space and label space, some kind of target function. The difference mainly lies how you prepare a data set. Of course, we're gonna have a like different learning paradigm, but then that will be different categories about learning procedure. Right? Okay. So let's return to the supervised learning framework, meaning that, okay, we're going to prepare a fully labeled training data set, and we hope that our learning model or algorithm will return you some learning function G. Right? So we see that, okay, we have some unknown ground truth target function F, right? We have learned some function G, right? So how can we see G is a good approximation to F? Right? First, we cannot really compare the two curves, right? Because we in most cases we don't know what is F is like, right? I don't know if F is sine function or cosine function or exponential function. This is something we do not know, right? And then how do we claim that our G is a good approximation to F? Yeah, exactly. Can you be more specific? Yes. So yeah, in practice, to evaluate whether our learning algorithm have found a good approximation to a target function F, we're not gonna draw some function curves in MATLAB or in Python and compare the curves. Instead, we're gonna draw test examples from the instance space. Okay? And we'll draw a finite number of test examples. We cannot draw infinite number of test examples, right? Then we'll look at whether the prediction made by our learned function is consistent with the ground truth. We expect that as long as we have a large number of test examples, and this discrepancy can be truly reflected. Right? That's the reason, right? If you just test the two examples, even your G of X gives correct answers, you won't trust it very much, right? Or if you test the 2 million examples, and in all the cases, like G of X gives like consistent prediction with F of X, you have a much larger confidence to say that your G of X is better than is very close to F, right? And this is kind of associated with generalization error definition. Later we're going to talk about, right? But here, let us just keep this intuition in our mind. So in practice, let me emphasize again, we're going to apply the model to many test examples and compare it to the target prediction to confirm your learned model is good. We'll give some good approximation to the target function. Right? So now I want to ask a question. So can we use test examples during training? No. Why? Yes. Right. I already seen the right answer. This is called cheating. Right. So why is this unforgivable in machine learning practice? Because you can easily create some simple algorithm, just memorize test examples and their labels, right? We'll test it, you get 100% accuracy, but it represents nothing, right? It indicates nothing. Right? So yeah, so please be very careful about this. Right? Everybody knows that, okay, I cannot blend test and training examples during the training phase, but many experienced machine learning engineering make such kind of mistakes. Right? So no matter when you got like high accuracy before you celebrate, just to double check if you happen to throw your test examples into the training phase. Any questions so far? Okay. So now let us summarize the general setting of supervised learning. So first, we're given a set of labeled training examples in the forms of pairs of instance and the label. And label is given by the target function, right? And this target function f is an unknown function, right? And typically, the input or instance, right, is represented in the so-called feature space or feature vector, because we have to represent in a numerical form. Right? We cannot directly throw a book to a computer. Right? The computer can only accept binaries. Right? You have to convert it to a numerical representation. For example, you might just use binary features to represent an instance, say like n-dimensional binary feature, or you just use n-dimensional real value features. So in practice, we'll always need to construct a feature representation of all the instances we're interested to classify or regress. Right? So this procedure is called feature engineering. Right? For example, giving you a pixel, right? Giving you a picture, which may be like 256 by 256. There are so many pixels, right? And then next step, before you throw it into your image, into your convolutional neural network, you need to consider, okay, how can I represent this image, right? You might first do some pre-processing and convert it into a representation. Say a matrix of normalized pixel values. You got 3 channels RGB, right? Or if you want to classify a document, right? A document, you should first represent those words in terms of, say, one-hot encodings or some kind of embeddings, and you combine them into a long vector, and then you throw it to some like logistic regression model or whatever other model to do classification. Right? This is called feature engineering. And once you have prepared X and FFX, the data set, right? The goal is to find a good approximation for the target function f. Right? And the label itself determines the kind of problem we have. If your label space only contains 2 labels, right? This is called binary classification. If your label space contains multiple classes, it's called multi-class classification. If your label space is continuous, this is called regression. Okay. That means you can regress your instance into some numerical value and some continuous value. It's called regression. For example, I want to predict the temperature tomorrow. Right? This is a regression problem. I want to predict what's my the price of my house, my real estate price. It's a regression problem. So you can see that actually the label space defines the type of problems. Right? Any questions so far? Example for multi-class classification? Oh, there are a lot. For example, the ImageNet computation, they got 1,000 or more than 1,000 types of objects like desk, chairs, cats, dogs, ladybugs, all those kind of stuff, and they just throw a picture to you. You want your convolutional neural network to predict the object, right? To be either, one of those 1,000 classes or some unknown object. Right? So there are many such kind of applications. Other questions? Okay, so when you start a supervised learning task, right? You want to consider the 5 problems in the below, right? So first, what is our instance space, right? What are the inputs to our problem? What are the features? How do we extract features? How do we use effective feature representation? And in fact, in practice, feature engineering, feature representation is very, very important. In many cases, like it kind of determine whether your model will succeed or fail. And what is your label space? Actually, is relates to the particular type of task. You want to do binary classification, you want to do multi-class classification, or you just want to do regression, right? What is our hypothesis space? Right? What is hypothesis space? Hypothesis space is the possible functional space with which you want to search over, right? So remember, we just talked about like the learning algorithm essentially is a function search procedure. Right? You want to search a function that best matches the training data set, right? And before the search, you need to indicate search range, right? That is called hypothesis space. For example, you can assume, okay, I believe my target function should be some linear function. Then my search space will be all possible linear functions, right? That's a hypothesis space, right? Or I believe my function must be differentiable functions, right? Second order differentials or third order differential functions, but they can be arbitrary, it can be linear, it can be nonlinear, right? And there's another hypothesis space, right? Actually, when you design your supervised learning algorithm, you should always be clear about what is your hypothesis space. Right? Although in popular algorithm, people have already known what their hypothesis space, like linear models, like small vacuum machines, kernel space, kernel method, and neural networks, right? But we request you still to be still clear about your hypothesis space. And what is your learning algorithm, right? What kind of searching procedure you're going to adopt? Right? That is called learning algorithm, right? And then what is our loss function or evaluation metric? Right? This is also very important because you need to measure whether your learning is effective or not, right? That's why you have to come out some metric. And also this metric can be used to guide your function searching procedure. Okay, taxonomy. We have seen this before, right? In our syllabus, right? We got supervised learning, unsupervised learning, semi-supervised learning, and we're gonna go through quite a few typical supervised learning algorithms throughout this semester, right? So we're gonna start with the so-called decision trees, right? And then we're gonna talk about how do we combine decision trees to form even more powerful learning algorithms called boosting and ensemble learning. Sometimes it's also called random forest, right? And then we'll talk about linear models, like a variety of different linear models, and then support back machines, and then talk about nonlinear models, kernel method, artificial neural nets. This is basically a plan, right? So we'll start with decision trees. Right? Why do we start with decision trees? Because it is the most intuitive machine learning model structure, right? It is so similar to how human beings are making decisions and sense the world, all kinds of stuff. So we believe that starting from it, everyone will feel comfortable. So we're going to first talk about the definition. So what are decision trees? And how decision tree represents the data. So you see that decision tree is not only some learning algorithm, it's also some kind of compression of data sets. Right? That's that will be an interesting view, right? But we'll see that later, right? Then we'll talk about the algorithm, right? How do we learn a decision tree? In other words, how do we create a decision tree out of from some training data set? Right? We're gonna talk about this standard algorithm called ID3 algorithm. So you see that essentially a greedy heuristics algorithm, but it is implemented in a recursive way. So it's very succinct but efficient. And then we'll talk about several variants or extension of ID3 algorithm to address some problems like overfitting issue. Right? We'll talk about what's the definition of overfitting, why it is bad in practice, right? And we'll talk about several strategies like post pruning, restrict the node splitting principles, and so on. And all those problems will also lead to the subsequent algorithm like random forest. Okay. Why decision trees is simple, intuitive, and we see that it's not only represents a hierarchical structure, but it also can be expressed as a set of rules. So that means decision tree, the interpretability is very, very good. Right? Why? Because it's just a set of rules, right? It's not like many popular machine learning models like deep neural nets. You don't know what deep neural net is learning, right? It just shows amazing performance in some tasks, but you never know why, right? And decision trees are much simpler, right? It's transparent. You know what exactly every rule represents. I actually give you some kind of hints, right? Why the mapping from the instance space and label space like that, right? This is very useful in many domains. Like people are not only pursuing high prediction accuracy, they're also pursuing the interpretability. For example, the medical prediction. If you diagnose someone with cancer, right, before you make them very frustrated, you need to let them know why, right? You cannot say, okay, my neural network tells me that you got cancer, right? That's not fair. Right? And also, decision trees has a very good potential. It can be promoted with very strong version boosting random forest, gradient boosting trees. Actually, gradient boosting trees are most popular algorithms used in online advertising companies like Facebook and Google and all kind of companies. Right? I got a friend in Alibaba, so it's kind of Chinese version of Amazon. It's very, very large, and even on larger scale than Amazon, right? And he's a senior research scientist. He told me that like although neural network is very hard, but they found that in practice neural network cannot beat gradient boosting trees. Okay. Plus, gradient boosting trees work very well even for a relatively small amount of data. So you can see that it's very useful and very powerful as well. Right? So these are just give you a sense that decision tree is very widely used. Okay. So let us talk about the first question. What are decision trees? We're going to first give a summary, right, to give you some impression. Then we're going to dive into some concrete example to tell you what are decision trees. Right? So to summarize, decision tree is a hierarchical structure that represents data with a divide and conquer strategy. Right? We'll see later what does this mean, right? What does it mean for divide and conquer, right? And each node in the decision tree represents a subset of the data. Right? So you see that from the root to down to the bottoms. Right? Every node in the tree represents a subset of data, and the root represents the entire data set. And the leaf, every leaf node represents the purest subset. Here, purest means that this subset should only have one label. And the nodes in the intermediate levels are kind of hybrid. They might have like multiple labels. And how is this tree grow, right? How does this tree grow or created, right? From the node, right? One branch is created for every value that the feature can take, right? Hence, for the partition the data accordingly. So this seems a little abstract, right? But later we'll see, right? We'll see the example, right? And leaves of the tree specify the class labels, the point to stop the partition, meaning that, okay, if I arrive at the leaf node and all the labels are the same, there's no need to further partition the subset of data. Okay, so then what is the goal of decision tree learning, right? In general, decision tree learning is to construct a decision tree from a given collection of label examples so that we can represent this data. That's the goal of decision tree. Right? So you can view it. Okay, when I construct decision tree, I'm not only constructing a prediction algorithm, I'm also constructing a succinct representation of the training data. Okay, any questions so far? Everyone is comfortable about this overview of decision tree? Okay, great. So now let us look at some concrete example. Right? Let us build a decision tree for classifying shapes. Right? Suppose we have collected a set of shapes. Right? They have different shapes. They have different colors. We have three possible shapes like ellipses, circles, rectangles, and triangles, right? And we have three possible colors: red, green, and blue, right? And those shapes, they have their labels, right? They have label A and B and C. Right? So we want to build a hierarchical structure, namely decision tree, to represent this label shapes, right? So before we build decision tree, I want to ask, what is the label for a red triangle? I just want you to ask you use your own eyes, right? By looking at those data sets, right? So now I want you to classify a red triangle. Which label do you believe? Any thought? Just look at those shapes, right? And try to extract some patterns or knowledge out of those shapes, right? And now, if I want to ask you to label a red triangle, which label are you going to use? What? B? Why B? Yes, right? That's very intuitive, right? We see that, okay, for the red shapes, looks like no matter if it is a circle or rectangle, it always have label B, right? So it's not irrational or unreasonable to give a label B for that, right? Okay, so now we're going to construct decision tree. We'll see that following our decision tree, we'll give the same label for red triangle. So before we construct a decision tree, we need to first look at how many attributes of those examples. Each shape has two attributes, right? Color and particular type of shapes, right? We got two attributes. Okay. The reason we ask this is because we're going to use the attributes to split data sets. So we notice that, okay, the attribute, we got two attributes for those examples, color and shape. Okay? And we can, in principle, we can choose arbitrary, we can start with arbitrary attribute, right? So here we're going to use color first. So how many colors do we have? 3 colors, right? So we can partition the data sets into 3 subsets according to the colors, right? So that means we're going to grow 3 branches, right? Green, red, blue, and each subset represents the shapes with the same corresponding color, right? So first, if we look at red shapes, what do we observe? Yes, all the red shapes have the same label, right? Label B, right? So that means we have arrived at a leaf node. Why? Because this subset contains the unique label, right? We don't need to split them anymore. So now we create a leaf node and tag the label B on this leaf node. And then let us look at the blue shapes. So the blue shapes here, 2 circles here, 2 triangles here, 1 rectangle here, right? So how many labels do they have? 3, right? So that means it is mixed. So we can further split them according to which attribute? Shape, right? So we can further split the blue shapes, right, into the 3 even smaller subsets. Right? So we got blue triangles. Right? First subset will be blue triangles. So for the blue triangles, how many labels do they have? Just one, right? Blue triangles are here. Just one label, which is label B, meaning that we can stop here, can create a leaf node, and we assign a label for this leaf node B. Right? And we can take a look another subset, which is blue square. Right? Blue squares, how many labels do they have? Just one, right? Which label? Label A, right? So that means we have to stop and create another leaf node, and we assign the label A. Right? So the remaining blue subsets will be blue circles. And how many labels? Also one, right? So which is label C. So now that we have a unique label for this subset, we no longer need to split them further. We just stop here and create a leaf node which has the label C. Right? So now we finish the growing about the left branch of this tree, right? And in the middle branch, we have finished. Now let us look at the rightmost branch, right? The green shapes, right? So how many labels do we have for the green shapes? 2 labels, right? 2 green rectangles here and 2 circles here, right? So it's still mixed. They are still mixed. So that means we can further split them with which attribute? Shape, right? So now we're gonna further split the green shapes according to the shape attribute, right? So now we'll give 2 subsets, right? One is green squares, the other is green circles, right? So let us look at the green squares. How many labels do they have? 1 label, right? What label? Label B, right? So that means, okay, we can stop here, no longer to split them anymore. We create the leaf node, we got label B, and let us look at another subset, green circles. How many labels? Just 1, right? It's label A, right? So that means, okay, we no longer need to split them anymore. We just create leaf node, we tag the label as A, right? Any questions so far? Okay. You mean how do we pick up the order to split the? Can you see it again? Mm-hmm. Mm-hmm. Oh, okay. So you mean even you exhaust the attributes, the subset might still not have unique labels, right? Yeah, it is possible. In that case, you have to stop, right? You don't have additional attributes. In that case, I can stop here. I create leaf node, but I'm gonna use the majority label as my label for that leaf node. This is the most common practice. Of course, you can come out other heuristic to assign label for the leaf. But again, at that level, you must stop because you have used up all the attributes. Okay, great observation. Any other question? Mm-hmm. 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 Yeah, that's a very good question. Actually, this is a follow-up question I want to ask. Yeah, but before we talk about that, what's your question? Yeah, that's a very good question. Here we just manually construct tree to give you a sense, right? But of course, which attribute comes first really matters, right? actually relates to how ID3 algorithm works. And it relates to the global goal that we want to make the tree to be as small as possible. Now, why should we make the tree to be as small as possible? Because of the so-called Occam's razor principle. We want to make our model as simple as possible. But if we want to enumerate the smallest tree globally, that will be too costly. That's why we come the greedy heuristics. But there's a long logic chain in the follow-up, right? Yeah, but it's a very good question. But anyway, let us first talk about your question, right? So first look at this tree, right? Can you come out a way to make a prediction? For example, if I want to predict the label for a right triangle, how can we do that? It's very intuitive, right? It's just starting from the root node, right? And there is associated test attribute, which is color. You say, okay, you just look at which branch matches this color because we're testing red triangle, right? So we follow this middle branch. And then we found out, okay, we have arrived at the leaf node. It tells me the label is B. Then I make prediction. So that's why using a decision tree to make predictions is very, very convenient, right? It's just to start from the root node, and then you just go through a path where each branch matches the attribute value in your test instance, right? And you find a corresponding leaf node, which tells you a label, right? Does it make sense for everyone? Okay, so now come to the problem, right? So what if we got a green triangle? Can we use our manually constructed tree to make a prediction? Seems not, right? Why? Because we're gonna stop in the middle, right? So we can just test it by ourselves, right? So for a green triangle, we start from the root node. We're gonna first test the color attribute, right? We know it's green, it matches the third branch. So now we arrive at this intermediate node, right? Now we're gonna test the shape, right? And now we know that, okay, the shape is triangle, and then we look for a branch that matches the triangle, right? Do we have such a branch? No, right? So I'm just stuck here, and we have no answer, right? This is actually a critical problem for this manual construction procedure, right? It is not robust, right? It cannot cover all possible test instances, right? So could anyone come out some remedy method? I'm just asking, right? Any thought? Show me first use shape. Okay. Yeah, this is definitely one way of doing that, right? But have you considered that? What if having some very bad cases, like even you switch the order, you can still not be able to cover all possible instances? How can we address that problem? That we need to make some strategy that in whichever case we're able to test, we're able to give a prediction for every possible instance. Yes. So that's a very good strategy. So in practice, when we later when you implement ID3, you'll see that we'll emphasize that again, right? No matter your subsets, so here is just the green shapes, right? The subset of green shapes, right? Even in your green subsets, we don't observe any triangles. We're gonna still create a virtual branch with triangle. But how do you choose label, right? And this label can be the majority label in green shapes or majority labels on the entire data set. It's up to you, right? So in this way, we're gonna create full branches for every possible splitting node. And so that, and even you don't have, you have empty subset associated with that, and you just assign some majority label. In this way, you can view like the tree is fully expanded, right? And you will always be able to give a prediction for any instance. Right? Just keep this like yes. Yeah. Later we will talk about ID3, you'll see that. So we'll have the recursive constructing procedure, right? For any split node, like splitting here or splitting here, right? We're gonna look over all possible attribute values. Right? For every possible attribute value, you're gonna create a tree, or you're gonna create a branch. Even for that specific value, your subset is empty. That's fine. If it's empty, I'm gonna stop there. I'm gonna create a leaf node. I'm gonna assign label them. Any other question? Okay, great. So now let us take another view about decision trees, right? So what decision functions do? What decision functions do decision trees represent? Right? So as we just discussed, right? Given a decision tree, we're gonna just look for a path which matches all the attributes in your test instance. As long as you arrive at the leaf node, you just use the label associated with that leaf node to predict, right? So then what does every path represent? It actually represents a rule, right? What does a rule mean? It just means a set of test conditions and then the result, right? So for example, this tree can be represented by this set of rules. Like you just enumerate all possible passes, right? So the first pass is color is blue and shape is triangle. Then you give label B, right? This first rule, right? And the second rule is represented by a second path. Color is blue and the shape is square. Then the label is A. Okay. And third pass represent third rule, like color is blue, shape is circle, the label is C. Right? So you can see that you can also represent the decision tree as a union of rules, a set of rules. Right? That's why decision tree is also popular for logic, like first order logic people. Right? They like decision trees as well, right? Because they just represent logic rules. Right? So the full tree is equivalent to the conjunction of all the rules. And then the learning of decision tree essentially is to extract a set of logic rules out of data. That's another way. So far the examples we have seen that is outputs are discrete categories, right? But what if you want to do regression? You got real valued outputs. Can we still use decision tree? Any thought? The answer is yes. Such trees are called regression trees. Right? And of course, the stopping criterion and the way to create the leaf node can be a little different, because if your label is continuous, right? You cannot say, okay, we're gonna stop when every instance has the same numerical label. That's not possible. Right? But you can make some kind of stopping criteria such that the subset of instances that have like similar labels, right? For example, their max and mean, their difference between max value and mean value is less than some threshold. Okay. Then you stop there, you create a leaf node, and then you might just take the average of the labels, which is numerical values, as your prediction. Right? And later we'll talk about how do we handle noise data, right? Noise in the labels, noise in the features, and then we need to prune the trees, because right now when we create the tree, we just want to create the tree to be as wide as possible, as deep as possible. In practice, you see that can cause severe overfitting. We don't want the tree to be too deep. So we also see that the branches seems are only created for discrete values, right? Suppose your attribute has 3 possible values, you create 3 branches. But what if your attribute values are continuous? A real value, for example, you got length as your attribute, height as an attribute, weight as an attribute. Right? How do we create branches for that? Any thought? Yes, exactly, right? So we're going to discretize those continuous values into a set of regions or set of ranges, right? We can either use some threshold or use some binning, choices, right? So that we can convert the numerical values into discrete values, right? Discrete features, like if this value less than 3, its value between 3 and 5, its value bigger than 5. Right? Actually, then convert it into discrete features, and then we based on this converted features to construct decision tree, right? So now we can take a look at this example, right? So we see that all those examples have 2 attributes, x and y, both are continuous, right? So how can we create a decision tree for that? We're going to first bin those continuous feature values, right, into discrete ranges, right? So for x, we're going to convert each x attribute into 3 possible features. If x less than 1, if x is between 1 and 3, if x is bigger than 3. You can see that we actually have 3 binary features for that, right? And similarly, we convert y feature into 3 binary features, and then that is equivalent to partitioning the feature space into several blocks, right? And then based on that, we can. Any question? Oh, I just random put it, right? In practice, the users have freedom to specify that. Actually, the range, how do you partition them, how do you bin them, is also related to your domain knowledge. Yeah. You can definitely do that. Yeah. And here I just give you one example, right? So for this example, right, if you use 1, 3 as the thresholding to bin those features, we got this decision tree, right? Of course, if you use other thresholds, we're gonna have other decision trees. Right? This is what the tree looks like. Right? An interesting thing we want to look at is the decision boundary. So what's the decision boundary? Decision boundary means the boundary which separate out your positive predictions and negative predictions. If we draw the boundary, right, which can separate, you can imagine like all examples stay in this XY space, right? And which are the boundaries which separate all the positive predictions, negative predictions. If you draw them, you'll see it will look like this. And what does it mean? It means that decision trees look like very simple, intuitive, right? But decision boundary are quite complicated. It can be highly nonlinear. So that means decision tree is very, very flexible and very powerful. Okay, to summarize, decision trees are a type of very compact data representation. And also it represents a set of rules. That's why people rule it as natural. It's like you take 20 questions survey and through your answers, you make some decision, right? And predicting with the decision tree is very easy because it essentially is to match the tree nodes and the branches until you find the leaf node, right? That's why in practice it's very popular. And clearly, given a data set, there are many decision trees that can represent Y. This is the last question before our Labor Day, right? Before. Yes, Exactly, right? So the previous example, we just start with color and then with attribute, right? So if you start with attribute with color, of course, they give you a different structure. Right? So actually, the orders of the attributes used to split and generate tree matters. Right? So then that comes a question, right? Which particular order of attributes should we use to generate tree? Right? That's what we're going to discuss in the next lecture, right? And here is one example that will show up in our next homework, asking you to manually construct a decision tree, use a different order, starting with shape and then color. Okay, see you on next Tuesday.